Okay, so let's start. Okay, so actually no new announcements today. I think everything is all set. Any questions that I need to? Okay, yeah. Talk to the TAs. Send email to the TA. You know which TA, who graded what. Just send email. Okay. So how about this? Oh. Okay. So we talk. One, two. Okay. Sometimes it works. Let's hope. Okay. Make some noises when you stop hearing. Okay, I'm gonna shout if it's not working. It's so we talked about really the learning paradigm that we talked about so far, one single learning paradigm that I can call error-driven learning. So we really learned from the mistakes that we've made. So we can think about it as there is some distribution D that we don't know over X cross Y, where X is the instance space, Y is the label space. And really, there is some data generation process governed by D of X, and there is a labeling process governed by some, again, a probabilistic process, D of Y given X. And that's what we see. We see labels X, XY. Labeled examples XY. So now, this is slightly more general than the way we talked about, but even though nothing really changes, we can think about it still as if there is some function, y equal f of x, that generates data, or the data is generated according to, or we can think about it as a noisy case. Either way, there is some probability distribution over x cross y, and that's what happens. So now notice that we don't assume that we know D. This is kind of the trick. The only thing that we always assumed is that the same D that generated the data when we learned is going to continue generating the data when we're being evaluated. And this is really the key assumption in all the learning theory we assumed. Notice also that if you know D, it's uninteresting, right? You know D, so you can just predict the most likely value of Y given X, right? So argmax over all possible Ys, case of classification, let's say 2 Ys, of D Y given X. So, and again, you can think about it as looking for a prediction Y, or you can think about it as looking for a function, hypothesis H. It doesn't matter. The same framework happens all the time, right? So in one case, you do argmax over the Ys. Here you're doing argmin over all the H's. You're finding the function that minimizes what you want to be minimized, which in this case is the expected error. So that's really what we've done before. And again, the focus is that we don't know the distribution. Under this scenario, there are really two approaches that we can take. What we've done so far is what I call direct learning or discriminative learning. And what we're going to start doing today is a framework that is called generative learning or Bayesian learning or probabilistic learning. You'll see it in different ways. So really, as you will see, the difference is not in what we learn. Everything that we want, we can learn one way or another, but rather the process and the assumption that underlie this process. So in the direct learning, let's take the case that we've seen several times during the semester, text correction, right? So we want to be able to, we look at example, and we want to know, is this text correct, or should we change it, correct a spelling mistake. For example, given a sentence, do we want to change it or in to in, and so on. So basically, the paradigm that we've adopted so far is we look at many examples. We discover some regularities in the data, and we use this to construct some policy, a prediction policy, some hypothesis. And this is a function that is really specific, right? It basically looks at features in the input, in X, and says something. Well, if you see a word D just after the target word, change the target word to in. And the assumptions that come into play are in the form of hypothesis class. We choose a function class, and we say we're going to learn into this class. Really, what we've done is, in approximating this function, we estimated this probability distribution, the probability of a label given X. That's what we've done. And we don't care about anything else beyond this probability distribution. How did we do it? We really drove everything from the error we've seen, minimizing the errors. And we generalized it a little bit using the notion of a loss function. We said that given a sample and a loss function, we're going to find something that minimizes the loss. The loss does not necessarily have to be the errors, but it's something related to the error because that's what we care about. And we define different losses. You know, this 0,1 loss was really minimizing the error, and the others were some other related loss functions that were easy to deal with and not quite directly minimize the error, but rather minimize something similar. And we got some guarantees, right? The guarantees are that if we find an algorithm that minimizes the loss on the observed data, then it's going to be good in the future. And good is something that is quantified based on the size of the hypothesis space that we have, and also a function of how many examples were we good at, right? The sample size that we had. And that's basically summarizing everything we've done so far. Now we're going to move to another paradigm. This new paradigm, we are going to think about the problem that we are facing through the mirror or through the view of we're going to generate data, and we're going to have some kind of model that generates the data, or we're going to try to learn the model that generates the data. And once we have this model, we can figure out whether data that we observe is good, is generated based on this, or not. And this is how we're going to decide whether to correct the data or not to correct. More specifically, in the case of text correction, we're going to learn, rather than learning a predictor for it or in, we're going to learn a probability distribution over sentences. This probability distribution will allow us to model the probability of I saw the girl eat the park, and learn the probability of observing the sentence I saw the girl in the park, and figure out which sentence is more likely. And now that we know which one is more likely, we know whether we want to correct, say we observe this one, whether we want to correct it to this one. So that's basically what we're going to do. Of course, in order to be able to estimate this probability distribution, we'll have to make some assumptions on what probability distributions could be, because there are too many probability distributions. But essentially, the guarantee that we have is that we make the right assumptions. Again, not on one specific probability distribution, because there's no learning problem, but rather on the right family of probability distribution. And then the learning problem is going to be, or one instance of the learning problem is going to be, learn the specific family, the specific member in this family of functions. So we're going to make this specific as we go today. But the bottom line is that in the generating paradigm, we are approximating a joint probability distribution over the instances x and the labels y. And this is why we call it generative. Really, we call it generative because we make an assumption on how x, the data, is being generated as a function of y. So if y is 0, 1, good or bad, you have an assumption of how good instances are being generated and an assumption of how bad instances are being generated. And this assumption is going to allow us eventually to learn this probability distribution and eventually also to make predictions. So this is why we call this generative, and we're going to see a lot of examples as we go. So before we start, I want to make one comment just to make sure that it's clear what we are doing. So you can think about probabilistic learning in a couple of ways. One way to think about it is, I want to learn a probabilistic concept. I want to learn a concept, which is really, concept is a function that maps x to 0, 1, or to the range 0, 1. And I'm going to interpret this C of x as the probability that the label is 1. The label of x is 1, right? So if the probability is 0.2, if the number here is 0.2, the probability the label is 1 is 0.2. If it's 0.99, I think that the label is 1. So even though this is a probabilistic concept, everything we said so far in the course applies. Basically, we are learning a function. We have to generalize a few things because our learning theory, for example, for the case of infinite functions, went through VC dimension. And VC dimension, the way we defined it, applies to discrete functions, right? We talked about dichotomies. So VC theory can be generalized to deal with real-valued function, where essentially the idea is that you discretize the real-valued function. Once you have discrete functions, almost everything we said goes over as is. There is a lot of papers to write, to fill this gap, but the ideas are the same. So everything we said about learning theorem applies to these functions. So that's not what we're going to do starting today. What we're going to do is we're going to do Bayesian learning, where we're going to use probabilistic criterion in choosing the hypothesis. So the hypothesis could still be deterministic. It could be probabilistic. It could be a Boolean function. It could be whatever you want. So what we're changing is not what we are learning, but rather how we're learning. Okay? So this is the important distinction. We could have learned functions before, and we may learn Boolean functions. In fact, we will learn Boolean functions today and next time, but the way we're doing it and the assumptions underlying this process are going to be different. Okay. Questions so far? Okay, so let's start. So really, there are a few ingredients underlying Bayesian learning, and in fact, you know all of them because you've taken a basic probability theory class. The only thing you may not know is how to use it in the context of learning. Our goal is going to be to find the best hypothesis still from some space H given observed data. Very similar to what we had before. We have to define best. And the way we're going to define best is most probable. In order to define it as most probable, we need to have some probability distribution over all the options so that most probably will be well defined. In order to push this direction, we will also have to have some notion of what's the relation between the data that we observe and the hypothesis, right? So think about the case of a coin, right? So if you toss a coin many times and you want to be able to make a prediction, for example, what's going to be the next toss, in order to substantiate something like this, you should have an idea of what's the relation between what you observe and the probability distribution of the options, right? So let's say the options are, I have a biased coin, it always gives heads, or probability 0.9, it gives heads, or I have a fair coin, 0.5, 0.5. If you want to observe a sequence and then make a prediction, you have to know how to relate the observations to these probabilities. And we're going to see what I mean in a concrete way. So we are going to be Bayesian about these things, which will, and you will also see that we can be Bayesian about many things. And this will matter. I mean, what we are Bayesian about will matter. So these are the 4 ingredients that we have to understand. which are at the basis of Bayesian learning. So, as I said, we need a probability distribution over hypotheses. We're going to start with P of H, which is a prior probability of the hypothesis. This is basically what we know before we've seen any data, right? Our assumption, our background knowledge, and sometimes we'll just assume that it's uniform because we have no idea how to prefer one H over another. P of D is going to be the probability of the data. Here's a sample of data. What's the probability of observing this data? Again, in this case, this is unrelated to the hypothesis. The probability of observing this sequence of coins. The probability of data given the hypothesis is the probability of observing this sample if the hypothesis that generated it was H. So this is really a key assumption that we have, the relation between hypothesis and data. And finally, what we care about is really what is called the posterior probability. What is the probability of H given D? This is the quantity that will allow us to eventually choose H. It's the probability that H is the target function given that we observed D. So these are the four components. And then they are related using Bayes' rule, which again, you all have seen, probably with slightly different notation. So Bayes' rule says that P of H given D, the probability of the hypothesis given the data, the posterior probability of H, is P of D given H times P of H divided by P of D. And again, you know this. You can just think about it again, and it will make sense to you that P of H given D increases with P of H, right? If nothing else changes, and you look at a more likely hypothesis with a higher prior, then the posterior is also going to be higher. So this makes sense. It also grows with P of D given H, right? So if the data that you observe is more likely, given my current hypothesized hypothesis, then the hypothesis is more likely. And also, it makes sense that it decreases with P of D. Why does it make sense that it decreases with P of D? Any intuition? Yeah? Yeah, so if the data is likely anyhow, it doesn't give you more information, doesn't make this specific hypothesis more likely. Okay. And in order to do whatever we're going to do here, we need to know a little bit of probability. And again, I know that you know all this, and you've done the exercise last night, and which kind of brought everything to the top of your head. Just to remind you what we care about. We care about product rule. This is, by the way, just Bayes' rule. It's the same thing, right? But you might have seen it this way. We care about the notion of independence. We need to know what does it mean that events are independent. We will later on also talk about conditional independence, which are introduced separately. We need to know the sum rule. We need to know Bayes' rule, which, as I said, it's just another way of writing the product rule. Again, if something here is not completely sort of easy for you, just revisit it and play with it. We need to know the total probability formula. So if AI are mutually exclusive events, that is, disjoint events, and together should be P of AI is 1 here. Together they cover the space. Then we can take an event B and think about it together with the AIs, sum over all I's. And this is the way to represent the probability of B. And the same thing could happen if you condition B on something. So P of B given C, again, we can decompose it by thinking about B together with AI, sum over all i's, and we can represent this way. So these are two things that, you know, you'll have to feel comfortable with because we're going to use it several times. Okay, so now let's start thinking about learning. So the only tool we have is Bayes' rule. In fact, we are done with Bayesian learning once we understand Bayes' rule. The only question now is really modeling. I mean, how do we model learning scenarios using this rule? Step one. And step two is going to be how do we represent probability distributions so that we can deal with it. So here is the learning scenario. The learner has a set of candidate hypotheses, which we may call models, and tries to find one of them, the one that is most probable, given the observed data. We're going to call this maximally probable hypothesis a maximum a posteriori hypothesis or MAP hypothesis. And this is how we're going to use Bayes' rule. So the maximum a posteriori hypothesis is going to be the one that maximizes P of H given D over all possible H's. Using Bayes' rule, I can write this as P of D given H, P of H divided by P of D. Again, I'm maximizing this over all possible H's. Now notice that in the denominator, I don't have H. So the argmax of this product is the same as the argmax of just the numerator. So that's it. So we are done with Bayes learning. All you have to do is decide what is the collection, capital H, be able to compute P of D given H times P of H for each element in this capital H, and choose the maximum one. That's it. The rest is details. The rest is what capital H's do we want to use, and how do we do this argmax, and so on. So let's start with some details. So in fact, before details, one more definition. So we are after this H map. However, sometimes, often, we don't have good prior information. So we cannot distinguish ahead of time between different H's that are members of capital H. I feel that this isn't working anymore, right? It's working? Okay. So we may assume uniform probability distribution. So P of Hi is equal to P of Hj for all I and j. In this case, basically, what happens is that we drop this because they are all the same, P of H's. So really, what we are doing is argmax of P of D given H. We're going to call this the maximum likelihood hypothesis. Okay, so it's basically the H map for the uniform case. Notice that what happens here is that we're saying the chosen hypothesis, the most likely hypothesis, is the one that best explains the data. Right? So you try each one of the H's that you have, and you ask him, I think let's try again. Now it works. Let's give it a few seconds. So far, so good. New battery. Okay, maybe change it there. It's sometimes, depending on the angle here. Okay. Thanks. This one still says it works. No, okay. Yeah, let me just answer your question. Okay. So what this says is that compute the probability of the data given H. The data is fixed. Try several H's and compute the probability of the data given each one of these H's. Choose the one that gives you the highest probability. I don't understand what consistent is.
So, for example, if H is
Right, okay, so you're right, and in fact I'm going to try in a case like this. So let's move to that example and then see. Before we move to this example, let's just take a simpler case. Let's just toss coins, just to make sure that we understand this. So let's assume that I have two hypotheses. I have a coin, and I have one hypothesis is the coin is fair, another hypothesis is the coin is biased, 60%, 40%. 60% in favor of head. So the learning problem here, choose the bias of the coin. Right? So again, it's the Bayesian learning paradigm. I have a hypothesis. In this case, it's a very simple problem, just two hypotheses in my class. And I have to choose which one. And the way to choose it is to use the data. I'm going to look at data and see which one is better. These are my hypotheses. H1, P of H is 0.5. H2 is P of H is 0.6. In order to use Bayes' theory, I need a prior. And I'm assuming here that my prior is 0.75 in favor of the fair coin. I need data. I did one experiment. I got head. And I need the key thing. I need a way to link observations to the hypothesis. This is the heart of everything we're doing. If we don't have this, we cannot use Bayesian theory. I need to know how do I model the data. This is the generative component, right? How is data being generated given the hypothesis? And I'm going to give it to you. And in fact, you know that if I'm assuming H1, the probability of observing this data is 0.5. If I'm assuming H2, the probability of observing this data is 0.6. Agreed? And again, I know that you know this. The important thing is that you think about it now as this is the generative component of my model. Very simple model, but you're going to do exactly the same thing when the model becomes more complex. Now that I have this, I can even compute the probability of the data. In fact, you will see in a few seconds that I didn't have to compute the probability of the data. because it's not in the formula here, you see? It was in the denominator, and I didn't need the denominator, but still it's a good exercise. How do I compute the probability of the data? Using the total probability table formula, right? So the probability of the data is P of D given H1 times P of H1 plus P of D given H2 times P of H2, which you can compute, and you'll see that it's this. It's also interesting to do a sanity check here. Does it make sense that the probability of the data of observing head is more than 0.5? Why does it make sense? Because, you know, one assumption I have is that it's 0.6, the probability of head. So it makes sense that the data is more likely to be head given these assumptions. Okay, so now the key thing is let's compute P of H given D. And what is P of H given D according to Bayes' rule here? It's P of D given H times P of H divided by P of D. And so for H1, I get 0.714. For H2, I get this. Now notice again that I didn't have to do it. I could have just computed the numerator here, the numerator here. I will not get two numbers that sum to 1 because they are not probabilities now, but still I can do the argmax. Okay, so now that we understand this, we know that we are still in favor of H1. That is, we still think that what was H1? H1 was that it's a fair coin, but less than before. Right? Our prior was 0.75, now it's less. Now, notice that if we were to use maximum likelihood, basically that means drop the priors, use the priors 0.5, 0.5, we would not think so. We would actually, because we saw H, we would think that the 0.6 H is a more likely hypothesis. And you can try it. You can also try what would happen if you toss your coin 100 times and get 70 heads. Clearly, you will believe that the coin is biased. I think I have these numbers here, but you can do it. So just check that this is what you get. Really, what I got here is that we are sure that after these experiments, 100 experiments, that H2 is a lot more likely than H1. Okay, so really we overwhelmed the prior. Right? We did 100 experiments, and the prior doesn't matter anymore. Okay, so that was one kind of the simplest possible scenario of Bayesian learning. Let's answer your question now. So in order to answer your question, I'm going to go back to what we did in the first part of the class and think about the concept class and think about it from the perspective of Bayesian learning. So what was the scenario there? We assumed that we were given a concept class C. We're given examples, training set, labeled according to a member f in this function, a collection of x, f of x. And my goal is to identify h that is consistent with f. But I'm going to do it the Bayesian way. What does it mean that I'm going to do it the Bayesian way? Let's write down all the 4 ingredients. What is P of H? The prior probability of the hypothesis. Let's assume uniform, right? I don't have a way to choose to prefer one H over another. What does it mean that it's uniform? It means that it's 1 over the size of H. I'm assuming I have a finite number of hypotheses, right? That's the prior probability. Okay, P of D given H, the probability of the data. given the hypothesis. Let's take one example first. The example XL. What is the probability of observing XL given H? So I'm claiming that the probability could either be 1 or 0. It's 1 if H of X is actually equal to L. Otherwise, it's 0. This is just by definition, right? So if H of X is not L, I will never see this example, right? Because I got a set of examples consistent with the target function. So the probability is going to be 0. I will only see examples that satisfy this. So this is for one example. Exactly the same thing is going to happen if I have a set of examples. It must be that all of them are consistent with H for P of D given H to be 1. Otherwise, it's 0. Third component, the probability of the data. So I'm just using the total probability table formula here. For a set D of examples, what is P of D? Sum over all hypotheses, P of D given H, P of H. Now notice, P of H is 1 over H, 1 over the size of H, right? For each one of them. P of D given H could be either 0 or 1. If the data is consistent with HI, it's 1. If the data is inconsistent with HI, it's 0. So essentially, I'm going to have here 1 for each consistent hypothesis and 0 for the rest. So essentially, what I'm doing here is I'm counting how many consistent hypotheses are there. 1 for each one. So what I get here is the number of consistent hypotheses, which is this, what I'm writing in the numerator, divided by the size of H. Okay? And finally, I'm going to compute the posterior. So I'm using Bayes' rule. The P of H given D is P of D given H, P of H, P of D. And let's see what do we get, right? So P of D given H, as we said here, could be 1 or 0. 1 for consistent hypothesis, 0 for non-consistent hypothesis. P of H here is 1 over H. This guy is 1 over the size of H. And we are dividing by P of D, which is this. So H goes up to the numerator. H consistent goes down. And the size of H is canceled. So what I'm going to get is, for the consistent hypothesis, if H is consistent, irrespective of what the name of H is, all the consistent hypotheses are going to give me this. Are going to give me that the probability of H given D is 1 over the number of consistent hypotheses. Otherwise, it's going to be 0. So essentially, we just syntactically played with the theory, and what we got, hopefully, is not surprising. What we got is that, as far as we are concerned, all the consistent hypotheses are equivalent from our perspective. We can choose any of them, and all the non-consistent hypotheses, we don't care about them. Yeah? It's 0. So because I have a data set, right? So if some of them are implausible, I can never see the sample. So I'm assuming consistency here. It is just a game to understand the notations, really. Okay, so basically, as I said, we are done with Bayes learning, and we're going to do more examples. So here is one slightly more interesting example than the coin with 2 values. I'm assuming a language, very, very simple language, a language that has 5 characters and a space. At any point, we can generate a sentence, if you want, in the language this way. we can generate PA with probability P1, P2, PB with probability P2, and so on, and P space with probability P6, where the sum of all these PIs is 1. Right? At any point, I can generate one of these things. That's my language. Now, this is an example of such language. You know, therefore, infinitely many probabilistic models like this, because I can choose the PIs any way I want. And the generative model is basically this. So now I'm writing the model for a collection of k characters. What happens if I've seen a sentence of k characters? Really what I've seen is, I'm asking is what's the probability of p of x1 up to xk? Because I'm generating characters independently, I can write this as p of the product of p of xi's, where xi ranges from a, b, c, d, e, and space. That's it. Very, very simple model. And the only question now is, okay, the learning problem is, give me the PIs. Observe some characters that were generated according to this model, and tell me what the PIs are. Yeah. U is, in this case, is these k characters that I observed. Well, really, there's no notion of a sentence here. I didn't. No, it could be. Yeah, I did not say that x1 is different than x2. So the most trivial model you can assume. And I also didn't say that I don't have several spaces here. Space to me is just one other character. The real issue here is that what I'm saying is that given data here, I should be able to, or given two strings, one goal could be tell me which one is more probable. In order to do this, I really need to compute the probability of each string, u and v. And in order to do this, I need to compute the PIs. So you can just look at this and tell me which one is more probable that I've observed. And for this, you can probably say something that, many B's is not so good as many A's. So probably this guy is more probable than this guy. So learning is learning the parameters. So now we have to start thinking about, okay, so how do I learn these parameters? How do you know what is the probability of A once you observe a lot of data? Yeah. So I give you a lot of data. Let's assume that I give you 100 characters. All of them are A. What's P of B? You will probably assume it's 0. If I give you 100 characters, half of them are A, half of them are B, you will probably assume that P1 is a half, P2 is a half, and the others are 0, and so on. Basically, that's the learning problem, to assume that, to estimate the PIs. Once you estimated the PIs, you know everything. That's, I don't know, but let's do it now. I'll ask you the same question in a more simple scenario, and you can suggest your answer. So the simpler scenario, maybe almost identical, is this. I'm tossing a coin. The coin has two sides, P, 1 minus P. That is, the probability of head is P, the probability of tail is 1 minus P. I tossed it m times, and I got k heads. What is P? So you also had an answer before, right? What was your answer for P? k divided by m. Everyone agrees with this estimation? I actually think that the probability is a quarter. Why is your assumption better than, your estimation better than mine? Yeah? Right, so same answer. So basically, the reason you think that m over k makes sense is because your intuition is that this is the most likely estimation given the data that we observe, this data, k out of m. So let's prove that. So so the only game we're playing today is the maximum posteriori or maximum likelihood game. So why is it the right answer? So in order to do it, we're going to compute. Okay. So if P is the probability of head, the probability of the data is this. It's important for us, as I said, to compute the generative probability, which is P of D given P. Hopefully you agree that P of the data given that the hypothesis is P is P to the K 1 minus P to the M minus K. Right? Notice that here I have infinitely many hypotheses, unlike the simple case before, where I had H1, 0.6, H2, 0.5. Here I have any number between 0 and 1 could be P. And this is P of, now I want to maximize this as a function of P. In order to do it, it's easier to work with the log likelihood. But we know that the value of P that maximizes this is going to also maximize the log of this, right? So I can take the log. I get K log P plus M minus K log 1 minus P. And I want to maximize this. To maximize this, I'm going to compute the derivative with respect to P, which is K over P minus, because of this, M minus K1 minus P. And I want to ask, when is this equal to 0? If it's equal to, when it's equal to 0 and you solve for P, you'll get K over M. So magically, your intuition was correct. But why was your intuition correct? Two reasons. One is I assumed a specific model. I assumed a binomial model, right? Under the assumption of the binomial model, I got that P of D given P is this. Right? So I assume a specific family of distribution that is the generative distribution. I could assume another distribution, and then your intuition would have been incorrect. You just assume binomial because it's the most natural thing to assume here. But in the problem set, I think, we'll ask you to assume something else, and you'll see that you don't get the same answer. So that's one thing. The other issue is, notice, what did I compute here? What is K over M? This is the most likely. What kind of problems could be in this case with this estimation? Yeah? Very small sample. I just tossed the coin twice, and I got 2 heads. What's the probability of tail? 0. Probably not right. So what we want to do is we want to do some kind of smoothing. And smoothing is really crucial, as we'll get to a little bit later. And by smoothing here, I mean do something to deal with the fact that you have small samples. So notice that I was a little bit cheating here. I did not compute maximum a posteriori. I assumed I disregarded priors. One way to introduce smoothing in a principled way, you can also introduce it in a non-principled way, and probably it will be the same at the end if you're doing it right. But to do it in a principled way is to assume a prior, and we're going to do this also a little bit later when we get to naive Bayes algorithm. But it's important to realize that you have to deal with it somehow. So we are going to do something to smooth away k from 0, or smooth k away from 0, so that we'll get an estimate also in cases where we observe zeros or just have numbers that are too small. Okay, so I already mentioned the notion of probability distributions, and we're going to deal here with, depending on which probability distribution you deal with, you actually make different assumptions, you'll get different results. So let's just refresh your memory with a couple of probability distributions that we're going to play with. Here is one. We already talked about Bernoulli distribution, right? So a random variable takes two values with probability p and 1 minus p. Binomial distribution is a very related probability distribution where the random variable takes one of n values, and you can think about it as the number of successes in Bernoulli trial, right? So you run the Bernoulli from here n times, and you count how many successes you had. It could range between 1 to n. So given that, the probability of getting k is p to the k, 1 minus p to the n minus k, and this is n choose k. And of course, you know this, right? So x, which is binomial np, n trials, each with probability p, for heads, let's say, is the sum of these Bernoulli trials. Another important family of probability distributions is multinomials. So let's start with categorical. So x could take values 1 to k, with probability p of x being I is pi, and the sum of the pi's is 1. Multinomial is, we have a random variable where xi tells me how many times I got I. Okay? Different than before. How many times I got I, where I ranges from 1 to k. So if I had k experiments, x1 up to xk, here n is the number, n trials, and the outcomes are x1 up to xk. P here is a vector of probability distributions of numbers, p1 up to pk. Then the probability of making these observations is p1 to the x1 up times p2 to the x2 times pk to the xk times n factorial divided by the xi factorials. Again, something that you've seen before. And again, you can think about the relation between binomials and Bernoulli is exactly the same way as the relation between multinomial and categorical. Okay, so this is something you know. Now let's see how we use it in the context of what we are doing here. So I'm going to take a case of Bayesian learning and try to make predictions, learn models and make predictions. So the case is going to be a case of generating documents. So I'm going to have a collection of documents. My language consists of 3 characters, or 3 words, A, B, and C. That's all I have in my vocabulary. I'm assuming that each document has exactly n words, just because it's easier for the way I'm going to model it. And here is the problem. I'm going to be given a collection of documents, D1 up to DM. Each one is labeled YI, where YI is 0 or 1, representing good document, bad document. Document I like, document I don't like. Okay? So you could imagine what would be the learning problem here. Eventually, you're going to give me a document and ask me to classify it. Is it a good document or a bad document? And now what we're going to try to do, I'm sure that you already have an idea of how to use perceptron to do this. But you have to realize that if you want to use perceptron, you have to make some assumptions, right? You're going to make an assumption of hypothesis space. What will be the hypothesis space that you will use? Yeah. Linear separators, but you have to make slightly more specific assumption. Linear separators over what? Right? You also decide what is your feature space. What could be your feature space? Right, so every document could be represented as how many A's, how many B's, how many C's. 3 dimensions. And you learn a linear separator on top of it. This could be something that you could have done earlier in the class. Now we're going to do it somewhat differently. And you can think later a little bit about what's the relations between these two. So what are we going to do now? So we're going to make the model more explicit because we want to learn it. So as I said, it's going to be a multinomial model, so, which means that the model uses multinomial distribution. So let AI, BI, CI be the number of times I'm observing A, B, and C in the document, in the ith document. And so this defines the data, right? This is the data I'm going to observe. And I have to give you the generative probability. Okay, so before that, my assumption is that the sum of AI, BI, and CI is n. And this is the generative probability. So I'm assuming that the probability of observing DI, given that its label is 1, is alpha to the AI, alpha 1 to the AI, beta 1 to the BI, gamma 1 to the CI, times n factorial divided by AI factorial, BI factorial, CI factorial, where here I'm assuming that the alpha are the probabilities for observing A, B, and C. Alpha is for A, beta is for B, gamma is for C. Okay, so my model consists of these 3 parameters. In fact, I need 6 parameters because I need the same thing for y equals 0. So I have 6 parameters that define my multinomial problem. Okay? So now I don't know alpha, beta, and gamma. The alpha 1 and 0, beta 1 and 0, gamma 1 and 0. I don't know them, but I know that this is the form of the model. Or I'm assuming this is the form of the model, right? So once I made this assumption, I know how to write down the probability of D given the label. So that's my generative model. Really, to make things complete, I will have to assume also what's the probability for the label, right? So I'm generating a document this way. I'm going to generate, first of all, I'm going to decide, is it a positive document or is it a, how do they say, a good document or a bad document? If it's a good document, now generate it using alpha 1, beta 1, gamma 1. If it's a bad document, generate it with alpha 0, beta 0, gamma 0. Okay? So that's the generative probability. Now that I have this, okay, and I have some constraints, the constraints are important, and they're going to also make our life a little bit hard when we do the estimation, but they're necessary because every time I'm generating something. So here is the game that we are playing here. And this is really the message that I want you to get. Unlike the discriminative case, the perceptron, which you suggested before, the game is different. We made an assumption on how the data is being generated, right? We made the assumption that it's generated using a multinomial distribution with parameters alpha, beta, gammas. Once we made this assumption, when you show me documents, I should be able to estimate the alphas, betas, gammas. Once I have these documents, these parameters, I know exactly the probability distribution that generated the data, and now I can just answer your questions. Your question could be, tell me for a given document whether it's good or bad. Okay, that's the game we're playing. A little bit more specifically, so again, we're given this collection of documents over these 3-letter characters. What we want to do is to classify, right? So given a new document, determine y, compute P of y given t. And we're going to do it using Bayes' rule. In order to evaluate this, we need to know P of d given y. We need to know Py and Pd, but in fact, as we said, Pd doesn't import. So P of y is really the prior on how many examples are positive, how many examples are negative. Easy to estimate, because I have 2 y's only. To compute Pd given y, I need to be able to compute it, and this is where I need to know the parameters. I need to know the alpha, the 2 alphas, the 2 betas, the 2 gammas. The game is clear? So this is really what Bayesian learning is about. And the only difference between different things is going to be that sometimes the models are going to be simpler than this, like the coin, and sometimes they're going to be harder than this, and we're going to see a couple models that are harder. But it's the same process that you're going through every time. So let's make one more step in this. So how do we estimate these parameters? So in order to estimate the parameters, just like we did with the coin, only a little bit more algebra, we're going to write the most likely value of the parameters, and then maximize it. So as we said, we care about this thing. The product over all our collection of documents, P of y, comma d I. This is given to us. We're assuming that examples in our sample are independent, so we can really say that the likelihood of the data, or the probability of the data here, later it will be likelihood of the data. The probability of the data is the product of the probability of each sample point in the data. And now I'm doing the following trick. I'm denoting by this eta the probability that an example is good. And now I'm claiming that I can write the probability of y, comma di this way. I'm writing it as, this is the probability of generating an example if it's good, times eta to the power of yi. This is the probability of generating a bad one. You see I'm using the alpha 0, beta 0, gamma 0, times 1 minus eta to the power of 1 minus yi. So this is an important trick that you will see several times. It's an important trick that allows me to write the joint probability without knowing whether the outcome is 0 or 1. So I'm writing it here to the power of yi. If yi is 1, then this remains, and this guy disappears, right? Because it's to the power of 1 minus 1. So just what's written in this case, what's written here is 1. If, on the other hand, yi is 0, then I'm going to get this, and this one is going to disappear. Okay? So it's an important trick that allows me to write something joint without knowing what it's going to be. And you will see this. We're going to use this several times. So now I want to maximize this product with respect to each one of the parameters. To do it, first I'm going to compute the log of this product. So the log is just sum over what we have here. So in every case, I have some constant, which I don't care, and I have AI log alpha, BI log beta, and so on. And now I need to differentiate. So the first thing I'm going to do is I'm going to differentiate with respect to this eta, because it's easy. So when you differentiate with respect to eta, you will see that it appears only twice. It appears here, So I'm going to get yi over eta from this part. And I'm going to get minus 1 minus yi over 1 minus eta from this part. All the rest will disappear. Because all the alpha, beta, gammas are independent of this eta. Right? So they disappear. So I get this. And if I want this to be 0, I'm going to get that eta is this thing. Make sense? How do you interpret this? Yes, so you wanted eta to come out as the number of positive examples divided by m, right? That's a sanity check, really, what we're doing here. Eta is something you kind of could have guessed ahead of time. And we got it right. Now, in order to do the alphas and the betas and the gammas, it's a little bit harder because they are not independent. Right? So the sum of the the zeros parameters is 1, and the sum of the 1 parameters is 1. So it's a little bit more complicated. I think you can do it. And in fact, you may do it in one of the problem sets. Really, the trick is to represent, for example, gamma as a function of alpha and beta, and now do the derivatives. This is one way. You can also do it with Lagrange multipliers. But anyhow, so I'm not going to do this, but I think you can do this. But the lesson here was hopefully clear. The lesson is this is kind of the paradigm of what we are doing here. We make an assumption on how data is generated. Once we made an assumption on how data is generated, we look at the data and we estimate the parameters. So now we know exactly how data was generated, and now we can compute. Yeah. Okay, that's a very good question. This is really a crucial question. So ask this question again on when was it? On Tuesday. We're going to talk a little bit more about the relations between these two. Yeah. And I think, yeah, that's basically it. So let's stop here. Good place to stop. You can think about this question because this is really a crucial question. Okay, have a good weekend.